This DS represents the second portion of atomic structure, and that is Bohr's theory. What is Bohr's theory? We'll look at that, sure. And remember, this is discussion we are talking about. We are discussing NCERT. So, taking these questions as an excuse, we will not only re-examine Bohr's theory, we will discover the theoretical nuances, and we will have probably an in-depth analysis also as far as these questions permit. So, let's begin the session of NCERT discussion. What is the wavelength of light emitted when the electron in a hydrogen atom undergoes transition from an energy level with n is equal to 4 to energy level with n is equal to 2? Now, within an atom, I am told that there are many energy levels, yes. And see, how exactly are electrons arranged around the atom? Bohr says that there are different levels. N is equal to 1, 2, 3 and 4. And as long as electrons are revolving in these orbits, fixed orbits called stationary orbits, they neither emit nor they absorb any energy. Fine. They emit or absorb only when they jump from one shell to the other or one orbit to the other. In our case, I am being told that the electrons are jumping from n is equal to 4 to n is equal to 2. Now, when they jump from higher orbit to lower orbit, they emit a photon. And this energy of photon, is energy of electron in 4th orbit minus energy of electron in 2nd orbit. You take the energy difference. You take the energy difference of electron in higher shell and lower shell, and the difference of energy can be accounted for by the energy of photon which has been emitted. This is simple Bohr's theory, the theoretical background of Bohr's theory. Fine. Do we have a formula? Yes, we do. This is 1 by lambda, and lambda is lambda of photon. Please don't get confused between de Broglie wavelength of electron, which is also lambda, and photon. I'm clearly writing this. This is equal to RH, which is Rydberg's constant, into Z square 1 upon N2 square minus 1 upon N1 square. That is Rydberg's formula for spectrum. Lambda of photon emitted we have to find. Rydberg's constant is a constant, so we'll just take that. Z. Now, this is a hydrogen atom. Yes, hydrogen atom. So, Z is equal to 1 because Z represents the atomic number 1 upon N2 square. Where it has jumped to 2. So, 1 upon 2 square minus 1 upon 4 square, it has come from N is equal to 4. Rydberg's constant is approximately 10 raised to 7 per meter. Approximately. Actually, is 1.097 something, but roughly this. Can I solve this? Of course I can solve this. How much is that? 1 by 2 square, 1 by 4 minus 1 by 16. Now, 1 by 4 minus 1 by 16, it is simply 3 by 16. So, therefore, lambda photon will be 16 by 3 into 10 raised to minus 7 meters. If you want, if you can give you a more accurate value of Rydberg's constant also, and we can calculate that more nicely. That would give us, let me just do it for you properly. Lambda photon is 16 by 3 into 1.097. Just let me check. Rydberg's constant was in denominator. Yeah, it would be. So that would be minus 7 upon 1.097. This is how it would look like. Let's solve this out. Once with this, so many meters. And this comes out to be 486 nanometer on solving. You want to get to the exact number? How did I calculate? Calculation obviously is left to you. But if you want me to show the calculation parts also, well, I would love to help. This Please remember, although mathematical, but this is very essential part of numerical or physical chemistry, because if you're not comfortable with calculations, you will always be uncomfortable with these chapters. That is why I solve each of them, even the mathematical computations I show, so that you get more comfortable. How do I do it? Let's try this out together. Well, 1.097 approximately is 1.1, and 1 by 1.1 is approximately 0.9. This is roughly 0.9 actually we are talking about. So this is 16 by 3 into 0.9. 16 is 48. So this is 4.8 into 10 raised to minus 7 meter and 480 nanometer. 480 nanometer by gross approximations I get this, and if you do this very accurately you get 486. Well, be happy, we are pretty close.